This research paper introduces a groundbreaking approach to generating synthetic microbiomes with minimized pathogenicity, focusing on combating multidrug resistance, MDR, in infectious diseases. The proposed method consists of two distinct segments: enhancing the learning efficiency of a multi-class classification network and employing a Bayesian optimization technique for efficient synthesis of synthetic microbiome samples. The first segment involves constructing a multi-class classification network, where the primary objective is to enhance the learning efficiency of the network. An autoencoder generative model is also established, which can represent microbiome samples in a compressed, low-dimensional space and reconstruct them with minimal quality degradation. In the second segment, synthetic microbiome samples are generated using a Gaussian distribution in the latent space, leveraging the decoder component of the autoencoder. A Bayesian optimization technique is then applied to select variants for biological screening, aiming to maximize the identification of designs with restricted MDR pathogens based on minimal samples. 4 acquisition functions are evaluated: expected improvement, upper confidence bound, Thompson sampling, and probability of improvement. Each strategy prioritizes synthetic samples according to their MDR detection capabilities. The results indicate that expected improvement, upper confidence bound, and probability of improvement consistently produce synthetic microbiome candidates with significantly fewer searches than Thompson sampling. The dataset used in this study consists of 1985 samples and 1824 operational taxonomic units, OTUs, representing the microbiomes present. For each sample, the relative abundance values of the 1824 OTUs are determined. Data from 11 pasture-raised broiler farms in the southeastern United States with flock sizes ranging between 251,500 birds were used in this study. Pre-harvest, feces and soil, and post-harvest, SICA, WCRF, and WCRP samples were included in this study. This research aims to demonstrate the feasibility of creating bespoke synthetic microbiomes with customized MDR profiles, utilizing deep latent space mapping and Bayesian learning for efficient guided screening. The proposed approach has the potential to revolutionize the field of microbiome research, providing a more focused and efficient method for identifying synthetic microbiome samples predictive of reduced MDR. This research paper presents a comprehensive analysis of antibiotic resistance in Salmonella, Campylobacter, and Listeria isolates using a multi-class classification neural network. The study leverages a dataset consisting of 1985 samples, with each sample including information on the presence of these bacteria, their genetic markers, and antibiotic resistance profiles. To address class imbalance, the authors employ an oversampling technique combining random oversampling and the synthetic minority oversampling technique, SMOD. This approach allows for training an accurate model despite limited and imbalanced biological data. The paper also discusses the importance of diverse point selection in training neural networks to enhance model performance, generalization, and representation learning. The authors utilize a determinantal point process, DPP, to select diverse microbiome samples, which promotes diversity by assigning higher probability to more varied subsets. This method ensures that the selected samples are representative and varied, making them suitable for learning tasks requiring broad coverage over the microbial spectrum. In addition, the study explores the use of autoencoders, an unsupervised artificial neural network technique, to learn representations of input data in an efficient, compressed latent space. The goal of an autoencoder is to minimize the difference between the input and its reconstruction, allowing for dimensionality reduction and feature learning. The authors propose integrating this technique into their synthetic data generation architecture to improve the quality and diversity of generated data. The paper highlights the significance of incorporating diverse and balanced datasets in machine learning models to ensure accurate predictions and robustness. By employing advanced techniques such as DPP and autoencoders, the authors aim to develop a more effective approach for predicting antibiotic resistance in foodborne pathogens. This research has potential implications for improving public health surveillance and monitoring programs, as well as informing strategies for antimicrobial resistance management. The authors utilize an autoencoder architecture, comprising an encoder model that compresses the microbiome input into a latent code, and a decoder model that reconstructs the original input space, X. This autoencoder is trained to minimize the difference between the microbiome input and reconstructed microbiome output, forcing the network to capture the most salient features of the data. In the second phase, the authors generate synthetic microbiome samples from the latent space to find ones predicting low prevalence of multidrug-resistant, MDR, foodborne pathogens. They produce 100 sample latent variable datasets using two methods: Gaussian sampling, which assumes a normal distribution, and latent hypercube sampling, which ensures full coverage over the entire range of each input variable. This approach enables the evaluation of the capability to reliably regenerate benign microbial communities from any latent sample source. The authors apply Bayesian optimization to find microbiome samples with minimal presence of MDR foodborne pathogens. They construct a multilabel probabilistic Gaussian process regression model that predicts the presence of MDR pathogens from 0 to 1 based on a microbiome sample's features. The acquisition function decides which new candidate sample to generate next using a latent space decoder model of the autoencoder, aiming to gather the most useful information about the optimum. 4 acquisition functions are examined: Thompson sampling, probability of improvement, upper confidence bound, and expected improvement. These functions balance exploitation and exploration to efficiently identify microbiome samples with the lowest pathogen presence. The experimental setup and results for a multi-class classification model and an autoencoder model are presented in this section, focusing on predicting antimicrobial resistance in poultry microbiome samples. The multi-class classification model is designed to classify the antimicrobial resistance profiles of Salmonella, Listeria, and Campylobacter MDR, multidrug resistant, based on the diversity rank of training samples. To evaluate the model's performance, accuracy and kappa score metrics were used, comparing the results from a model trained with randomly sampled data against one trained with data ranked by diversity. Table I illustrates that the model's accuracy and kappa score improve when the training samples are ordered according to diversity. Figure 3 demonstrates the incremental improvement in performance at each step when training samples are ranked according to diversity, indicating that the order of training samples significantly influences the training accuracy. Additionally, the paper presents the use of a deep neural network for both the encoder and decoder models in the autoencoder setup. The autoencoder is used to recreate test data, which is then used to evaluate the multi-class classification model's performance. Table 2 compares the multi-class classification performance between the model trained with randomly sampled data and the model trained with data ranked by diversity, both on the original test dataset and the autoencoder recreated test dataset. The results show that the model trained with data ranked by diversity outperforms the model trained with randomly sampled data in terms of accuracy and kappa score, regardless of whether the test data is original or recreated by the autoencoder. The research paper delves into the application of machine learning techniques to predict antimicrobial resistance in poultry microbiome samples. It focuses on the utilization of a variational autoencoder model for dimensionality reduction and synthetic data generation, with an emphasis on enhancing the efficiency of this process through Bayesian optimization. The paper also assesses the efficacy of different acquisition functions in selecting synthetic samples that predict the lowest MDR levels. In terms of dimensionality reduction, the study demonstrates that employing a variational autoencoder model can significantly reduce the dimensionality of the dataset while preserving essential information. This is evident from the improved classification accuracy and kappa score when training samples are ranked by diversity as opposed to normal order. For synthetic data generation, the paper introduces a novel approach utilizing a variational autoencoder model to generate new samples based on the input data. These samples are then used to augment the training set, enhancing the model's predictive capabilities. The evaluation of this method shows that it can effectively improve the accuracy and kappa score of antimicrobial resistance prediction. The study also explores the realm of Bayesian optimization, comparing various acquisition functions for their ability to select synthetic samples with the lowest MDR predictions. The results indicate that different acquisition functions perform better under different conditions, such as the Thompson sampling method being most effective for datasets with highly disproportionate class counts, and the expected improvement, probability of improvement, and upper confidence bounds performing well in more balanced datasets. Lastly, the paper highlights the importance of specific microbiome features in reducing pathogen levels, particularly Bacteroides species and Ruminococcaceae family members. These findings align with ongoing research into the use of probiotics to promote a healthy balance of gut microbiota, which can lead to improved poultry health and productivity. Researchers have developed a novel approach to predict multidrug resistance in pathogens using synthetic microbiome samples. The study introduces a diversified multi-class classification method, enhancing the prediction capabilities of pathogens. This is achieved by implementing an autoencoder framework that generates synthetic samples with reduced pathogenicity, a breakthrough with significant implications for microbiome research and pathogen management. To optimize the iteration process, a Bayesian approach is adopted, allowing for more efficient progression in the research. The validity of the results is rigorously tested against reasonable baselines, ensuring the robustness of the findings. The study identifies key microbiome contributors influencing the studied phenotypes, corroborated by supporting research. The multifaceted framework demonstrates promising capability to elucidate and predict microbial community-level phenotypes relevant to food safety, human health, and disease. By leveraging synthetic microbiome samples, this approach offers a powerful tool for predicting MDR in pathogens, with potential applications in various fields. The study's findings contribute to a deeper understanding of the complex interactions within microbiomes and pave the way for future research in this area. I apologize, but it seems you didn't provide the content to refine. Please provide the transcript for the explainer video, and I'll be happy to refine it according to the guidelines. I'll transform the text into a direct, concise form suitable for voiceover narration, maintaining technical accuracy and depth, and highlighting novel ideas, significant findings, and important arguments presented in the original text.